Mathematical model of armature controlled DC motor. Armature controlled DC motor. This is the armature. But the armature resistance and inductance are mentioned here. A torque will be developed in the armature. That is called TM. The mechanical torque developed in the armature. That's why it is rotating. That's why it is rotating. What is back EMF? Back EMF. Back EMF is EMF generated in the armature of motor. Armature of motor. What is generator? If you rotate the armature in the magnetic field, EMF is induced. That is generator, DC generator. Because it cuts the flux, that's why EMF is generated. Here, the opposite. Fleming's left-hand rule. Magnetic flux is placed, you are rotating. Instead of placing, instead of rotating, we are placing in the magnetic field. Fleming's left-hand rule, that's why it starts rotating. But the coil is in the magnetic field. Right-hand rule also applied, no? Why it is rotating? Because the coil is placed in the magnetic field. That's why Fleming's left-hand rule, it starts rotating. But Lenz's law, and EMF is induced, the cause which produced opposes the cause which produces. Lenz's law. As per Lenz's law, there is a back EMF. That is generator principle. You can think like that. Even though it is a motor, the coil is rotating in the magnetic field. That's why there will be an EMF will be induced. That is back EMF. Therefore, if you apply a voltage EA across this armature, you are applying a voltage EA. There is a drop in the coil, that is LA DIA by dt. And drop in the resistance of the armature coil, RAIA. And there is a back EMF which opposes the applied voltage. So three components are there. Normally for a coil, only two components. Since it is rotating in the magnetic field, there is a back EMF EB. Therefore, EA equal to LA DIA by dt plus RAIA plus EB. This is because of the rotation. EB is because of the rotation. So the applied voltage EA equal to LA DIA by dt. That is potential drop in the coil, potential drop in the resistance plus back EMF. What is the torque developed in the armature? Torque, the mechanical torque developed in the armature equal to proportional to armature current. The torque developed in the armature is proportional to armature current. To make it equal, the KT constant. So TM equal to KTIA. That is the mechanical torque developed in the armature. But this armature is connected to a load. Connected to a load. That load has an inertia of J. Load has an inertia of J. and a dashpot V. Therefore, this mechanical torque equal to J d square theta by dt square plus d theta by dt. This is first equation. This is second equation. This is third equation. These are the three equations. Why it is called armature controlled DC motor? How we can control speed of a DC motor? How we can control the speed of DC motor? What are the methods available? N is proportional to V minus EV upon 5. So any change in V applied voltage, that is VA or EA, we can say. If you change this EA, there will be a change in speed directly proportional. That's why if you want to change the speed, if you want to control the speed of this motor, simply you can adjust this applied voltage. That is one way. Another way is if you decrease the flux produced by this coil. This is the flux given by this. For this armature, you need a flux. The flux will be generated by this field coil. This field coil will produce flux. If you adjust this flux to reduce the flux, that is reducing the voltage, you can reduce the flux. By that also you can increase the speed. If you increase the flux, there will be a decrease in speed. So in the opposite way, that is also possible. But here, if you adjust this applied voltage across the armature, then it is called armature controlled DC, because we are controlling the speed by controlling the voltage across armature. If you adjust the speed by adjusting the field, then it is called field controlled DC. We are not adjusting any field current. That's why there is no change in field. So this is constant. That's why we are not including this in the mathematical model, because it remains constant. We are assuming that field remains constant. Then why we have to obtain the mathematical, why we have to include? No need, because the equations are for changes. The equations are for changes that you will see later in the next semester. In process control, you study all those things. Now it's very difficult to explain. There is no change in the field. That's why there is no equation for that. But if you control by field, means that equation also will be improved. So only this equation is written already. That's all about electrical equation. For mechanical electrical relation, there is one equation. The mechanical torque developed equal to KT times IA, that is second equation. Then a mechanical equation, because the armature connected with a load whose inertia is J, dashpot constant is B. Therefore, Tm equal to, the displacement in the armature is theta. Therefore, Tm equal to J d square theta by dt square plus B d theta by dt. That we know. Already we studied for the rotational system, mathematical model of rotational system. So we got three equations. But we know that the back EMF, how back EMF is generated, a coil is rotating in the magnetic field. That's why there is an EMF induced. That EMF opposes the applied voltage. Lenz's law. So it is proportional to speed of that armature. Proportional to back EMF is proportional to speed d theta by dt. If you make it equal, you are multiplying by kb. Therefore, EB equal to kb d theta by dt. That is fourth equation. Instead of putting d theta by dt, you can put omega also, kb omega, or speed, number of rotations. Here, EB equal to kb d theta by dt. That's all. These are the four equations represent the armature controlled DC motor. Four equations represent the given armature controlled DC motor. Now, we will obtain the transfer function. For that, we have to take Laplace transform of this E A of S equal to LAS, assuming zero initial conditions. LAS IA of S plus RA IA of S plus EB of S. That is also a variable. This is equation A in frequency domain. Tm of S equal to Tm of S KT IA of S. This is second equation B. Next equation is Tm of S equal to J S square theta of S, assuming zero initial conditions. B S theta of S. This is another equation in frequency domain. To write for this EB of S equal to KB theta S theta of S. This is the equation. If you combine all these things together, you will get the transfer function. What is the input to the armature controlled DC motor? Transfer function model of armature controlled DC motor. So what we can do is here we can take this IA of S outside, and IA of S can be substituted from here. Then you can substitute Tm of S in that. Everything will be in terms of theta. You will get. Then EB of S, in place of EB, if you substitute this, you will get back EMF also comes in terms of theta. So we can write now EA of S equal to LAS plus RA multiplied by IA of S plus KBS theta of S. Why? Because D says EB equal to KBS theta of S. That's why we wrote KBS theta of S here. Now, IAS can be replaced by TM by KT. So LAS plus RA. IAS equal to what? From the equation B, we can write TM by KT. TM of S upon KT plus KB S theta of S. Now, TM equal to what? TM of S equal to JS square. Yes, JS square theta of S plus BS theta of S. So instead of Tm of S, we can substitute LAS plus RA. Instead of Tm, we can substitute this. We can substitute this equation. Tm equal to Tm of S equal to JS square plus BS multiplied by theta F S can be substituted. Therefore, instead of Tm, JS square plus BS theta of S upon KT plus EB, for EB equal to BS theta of S. So everything in terms of theta S now. Now we can find theta of S upon EA of S. So what we can do is theta, therefore theta of S upon KBS theta of S. Therefore, theta of S upon EA of S equal to, you bring everything here, what you will get? If you take KT as LCM, you will get KB KT upon KT. Am I correct? I am taking LCM KT. Therefore, here you will get KT in the numerator. KT in the numerator. In the denominator, you will get LAS plus RA multiplied by JS square plus BS plus KB KT S. That's all. So this is the transfer function model of given system. Transfer function model of given system. Transfer function model of given system. Once again, we'll see what is the armature controlled DC motor. DC motor can be controlled in two ways because we have the relation N equal to VEA minus EB. EA minus EB upon 5. Either you can control the speed by adjusting EA or by adjusting flux. The armature control DC motor, we are not adjusting the flux. Flux remains constant. That's why there is no equation for this field part. We are writing equation for this part only. By adjusting EA, we are adjusting speed. That's why it is called armature control DC motor. The first equation is, it has armature resistance, inductance, and back EMF. So therefore, the first equation is EA equal to applied voltage equal to LA DIA by dt. Because current through the inductor is IA, armature current, IA. Current through the inductor is, current through the armature is IA. Therefore, LA DIA by dt plus RAIA plus back EMF EB. If you take Laplace transform, you will get EA of S equal to LAS by assuming zero initial condition. LAS IA S plus RAIAS plus back EMF, if you write KB EB of S, sorry, EB of S. But EB of S equal to what? EB of S equal, EB equal to, we know that EB equal to KB d theta by dt. If we take Laplace transform, EB of S equal to KBS d theta. That is substituted here, KBS d theta for EA of S. We know that TM equal to KTIA because mechanical torque developed in the armature is proportional to armature current. Therefore, TM equal to KTIA. If we take Laplace transform, TM of S equal to KTIAS. That is second equation. We know that this armature is connected to a load whose inertia is J, dashpot constant is B. That's why the mechanical torque equal to J d square theta by dt square plus B d theta by dt. Because theta is the displacement. Theta is the displacement. If we take Laplace transform, Jm of S equal to Js square theta of S plus Bs theta. If you substitute in EA of S equal to LAS plus RA into IA of S plus back EMF equal to KB S theta of S. From here, from D equation we substituted. Now, IA equal to what? From the TM equation, we can substitute IA equal to TM by KT. TM equal to TM equal to JS square theta of S plus BS theta of S. Therefore, TM can be replaced by JS square BS plus theta of S by KT. If you take a LCM using KT, the numerator also becomes KB KT S theta of S. So if you find theta of S upon EA of S, why we have to find? Because theta is the output. Sorry, EA of S. applied voltage is EA of S. If you find that from this relation, we can write that KT is the denominator, that becomes in the numerator, KT upon LAS plus RA multiplied by JS square plus BS plus KB KTS. That's all. This is the transfer function model of armature control DC motor. How this armature control DC motor is represented here by electrical circuit. Electrical representation, electromechanical representation. But I want to represent this in a block diagram model. Most of the equations will be represented in block diagram by transfer function model. So if I find the transfer function, this can be represented as a block diagram like this. I found the transfer function of the armature control DC motor, that is theta of S upon EA of S. That is the transfer function. Input is EA of S, output is theta of S. This representation is called block diagram. Block diagram, not black, block diagram. Block diagram, we can represent like this. We have put a box. The transfer function can be called as GA of S equal to theta of S upon EA of S. We can call the transfer function as GA. A is for armature control DC motor. GA of S. So in the block diagram, we can write GA of S simply. The input is EA of S and the output is theta of S. We can put like this. This representation is called block diagram representation, but there is no inner details. The final transfer function is represented like this. But we can find the block diagram for each and every equation. Every equation has input and output. For every equation, we can find one block. So we can, how we get this transfer function? By combining all these equations. So we need a mathematical manipulation is required. But if you represent each equation by a block diagram, we will get block diagram representation. Block diagram representation. That also can be used to find the transfer function. That we will see now. Now, what is the first equation? The first equation is EA equal to EA of S equal to LA S plus RA IA of S. Am I correct? Plus EB of S. This is separate. So instead of combining, because it is in different variable, this is different variable. So what I can do is, I can put EA of S minus EB of S as one variable equal to LAS plus RA multiplied by IAS. Let us assume that IAF is the output. EA minus EB, if you give EA minus EB as input, it will give IA current. That way I can represent the model, you know. So the output is IA of S. I am assuming that output is IA of S. Input is EA minus EB. I am leaving S EB equal to 1 upon LAS plus RA. 1 upon LAS plus RA. You got one transfer function. In this case, the input is EA minus EB, output is IA, armature current. I got one model. Block diagram representation. For this, I can put like this. One block I can put. It is called IA upon EA minus EB. The input is EA minus EB. output is IA. I can put. So this equation can be represented like this. Next equation, what is the next equation? Tm of S equal to JS square plus BS multiplied by theta of S. Am I correct? Tm equal to JS square plus BS theta of S. One more equation. Tm equal to KT IA of S. So what is the transfer function? If you take this, this is the equation B, this is C. So first let us see B. The input is IA, output is TM. TM upon IA of S. TM of S upon IA of S equal to KT. This is another equation. Another block diagram. What is the input for this? KT is the transfer function. Input is IA. Output is TM. This can also be represented in block diagram. Output is theta of S. Input is TM of S. That is equal to 1 upon J S square plus Bs. This is another block. This block can be represented like this. Theta of S upon Tm of S. Input is Tm. Input is Tm of S. Output is theta of S. So if we combine all these together, if you come, one more equation is there. That is for KB. What is EB equal to what? EB equal to KB S theta of S. Now we got how many blocks? How many blocks? For EB, we have to get one more block. EB equal to KB S theta of S. Therefore, what is the output? Output is S theta of S. S theta of S. Input is output is EB. Input is S theta of S. I am deliberately including that S. I'll tell later. EB of S. Output is EB of S. Input is S theta of S. S theta of S equal to KB. Equal to KB. Another transfer function. Another block you got. This block can be represented as KB. Input is S theta of S. Output is EB. If you combine all these blocks together, you will get the representation, block diagram representation of armature control DC. We will combine all those things together. What is the first block? First block is, this is the first block. First block is, what is output? IA of S. What is the input? EA minus EB. Let us take that first. So we will take that first. 1 upon LAS plus RA. What is the input given to this? EA minus EB is given as input. What is the output? IAS. Next block must be the input should be IA. If you go there, what is the input IA? Which block has input IA? This block. IA is the input. TM is the output. TM is the output. If you combine that, what you will get is, if you multiply this by KT, simply KT, input is IA, output is TM. Am I correct or not? This is the second block we are going to combine. Now, Tm is the input. If you give Tm as the input, you will get theta as output. Tm as input, theta you will get output. Let us put one S, we will bring that one S here. I am deliberately doing Js square plus Bs, In that I am removing one S here. 1 upon Js plus B. Therefore, I can write S theta of S. S theta of S here. Now, this is the third block. This is the third block. Bring that third block there. What is the input? Tm is the input. Output is S theta of S. Output is S theta of S. Input is Tm. Output is S theta of S. What is the transfer function here? 1 upon Js plus B. Now, one more block we are having. That block is if you give the S theta of S as input, you will get back EMF. You will get back EMF. So we will go there and take this and put that block. That block will give EB as output. What is the transfer function here? KB, that's all. If you multiply by KB, you will get EB. What is the input? S theta of S. So here, what is required here? EA minus EB is required. EA is what? Applied voltage. Applied voltage minus back EMF. So you can put a summing block here. You can put a summing block here. Two signals can be summed, subtract. Op-amp based summer, subtractor, adder, subtractor is studied. I studied operational amplifier, linear integrated circuits. In that, like that, one summer I am putting. In that summer, I am giving EA as input. EA as input for that summer, and another input is EB, that is in negative sign. So it is a subtractor. That's all. So what you are getting here, EA minus EB. EA minus EB. So EA minus EB is given as input. That will give IA as output. IA is given as input. TM is the output. If TM is given as input, S theta of S, that is velocity, angular velocity, S theta of S. S means what? Differentiation. S means d theta by dt is written as S theta of S. Therefore, S means differentiation. Therefore, this is angular velocity. So that angular velocity is given as input to this block. That gives back EMF. Here, S theta of S is the input. That gives back EMF. That's all. I represented the same mathematical model in block diagram representation. For one equation, one block. One equation, one block. So I got block diagram representation of armature controlled DC motor. Armature controlled DC motor. Now, S theta of S is not the output. Output is what? Theta of S is the output. So what I can do is I can put one integrator here. 1 by S means integrator. You can design integrator in linear integrated circuits. Summer, subtractor, adder, subtractor, integrator, differentiator, you studied. In that, integrator is 1 by S. Integrator. If you put the integrator, S theta of S becomes theta of S. Now, what is the transfer function? Theta of S upon E of S, EA of S. That is the transfer function. So this transfer function we got. This transfer function we got. Transfer function is, each transfer function is represented in terms of block diagram. How we got theta of S upon, EA of S. There I am combining all equations mathematically, and finally I found. Here also you can find. Here also you can find. Here, this is one block. This is second block. This is third block. In frequency domain, all the blocks can be multiplied. All the blocks can be multiplied. Therefore, if I multiply all the blocks together, I'll get KT upon LAS plus RA multiplied by JS plus B. I multiplied all the three blocks together. Now I can get the block diagram like this. I am simplified the block diagram like this. Now I have to remove this feedback, then only I will get the block diagram. For that, the formula is, now you take the formula, we'll see later. Suppose I'm having a transfer function like this, EA of S. Here, this is summer. I'm having a transfer function G. In the feedback, I am having another transfer function H. Here minus, here plus. What is the meaning of this minus? Negative feedback. In amplifier, you have studied that negative feedback only we have to give. We should not give a positive feedback. If you give positive feedback, it becomes oscillator. In oscillator only, it is positive feedback. If it is amplifier, means it should be a negative feedback. In electronics, you studied the same thing here also. So negative feedback. If you have the block diagram like this, if I want to remove this feedback, I want to make this as a single block, means this is equal to G upon 1 plus. If you have a minus sign here, you can write 1 plus. This plus sign is because of this minus sign. Negative feedback means 1 plus GH. So you can find a single block like this. If you apply the same rule there, what is the rule here? What is the rule here? In the numerator, put whatever in the forward path. This is forward path. Am I correct? Forward path. Input to output. You are traveling from input to output. This is the forward path. What is the transfer function in the forward path? That is in the numerator. In the denominator, what is there? 1 plus. Why I put 1 plus? If you have a negative sign, you would put 1 plus. Then in the closed path, this is the closed loop. The closed loop, what are the blocks are there that you put here? That's all. This is the formula. We'll see the formula later. G upon 1 plus GH. That's all. G upon 1 plus GH. If you apply the same formula in the previous block, here you apply the same formula, it becomes, I'll write KT upon LAS plus RA JS plus B whole divided by 1 plus KT KB. Why KT KB? There is one KT, this KB upon LAS plus RA multiplied by JS plus B. In addition, one more block is there that is left out, that is 1 by S. That's all. If you combine these two, this becomes single block. Then cascaded with another block 1 by S, so that can be multiplied. That's all. If you simplify this, whatever you got in the previous mathematically, that you will get the same. Now we have to take LCM. If you take LCM, what you will get is KT upon LAS plus RA multiplied by JS plus B whole divided by 1 plus, therefore, LAS plus RA multiplied by JS plus B plus KT KB whole divided by LAS plus RA multiplied by JS multiplied by JS plus B. So these two getting cancelled. I am taking LCM, that's all. These two getting cancelled. Multiplied by 1 by S. So what you will get here, KT upon LAS plus RA. If you bring that S here, you will get JS square plus BS plus if you bring that S to this also, KT KBS. This is theta of S upon EA of S. So we got the same what we got in mathematically. You see, compare with this, what we got mathematically, the same transfer function you got KT upon LAS plus RA, JS square plus BS plus KT KBS. You got the same. So theta of S upon EA of S is the transfer function. If you draw for each equation, if you draw a block and combine like this and simplify the blocks, you will get the transfer function. You will get the transfer function. Therefore, if it is mathematically so difficult, then you can represent each equation by each block and combine them like this graphically. Then you can find the transfer function finally. That is called block diagram reduction technique. That is called block diagram reduction technique. Block diagram reduction technique. Block diagram reduction technique. For that, some set of rules are there. Two rules we have seen already. 3 blocks are there. If 3 blocks are there, if 3 blocks are there, if 3 blocks are there, the 3 blocks can be multiplied, I said. That is one rule. Another rule, the feedback path can be removed like this, I told. That is 7th rule. First rule is all blocks can be multiplied. 7th rule is like this, we can, feedback path can be removed. That is 7th rule. Like that 7 rules are there. That we will see in the next class. Then we will take the block diagrams and we will reduce the block diagram into single transfer function. We'll see in the next class.